Hello friends, today we are going to look at another topic in numerical methods, which is called secant method. So secant method is another popular method to solve a nonlinear equation. So we have used Newton's method or Newton-Raphson method previously in one of our previous videos. And this Newton-Raphson method is a popular method as well, but this requires the derivative of the function f of x to be evaluated. In some cases, it is not easy to evaluate the derivative. In that case, we can use secant method in place of Newton-Raphson's method. Secant method also belongs to a group called open domain methods like the fixed point iteration as well as the Newton's method. Here the nonlinear equation f of x equals 0 could be an algebraic equation that consists of x, x squared and other powers of x, or it can be a transcendental equation that can contain, in addition to x and the powers of x, logarithmic, trigonometric and exponential functions. Some examples of nonlinear equations are given below. The first one is an algebraic equation and the second one is an transcendental equation. So the algorithm for the secant method is given below. So on the left hand side on the graph, there is a function f of x. Our objective is to find the root for the function f of x. The exact root is shown as alpha. So in secant method, we need two initial values. For example, x1 and x2, or in this case, in general, it's xi minus 1 and xi. So once we know these two values, we can draw a straight line through these points. And that line is g of x. So this line goes through these 2 points and intersects the x-axis at xi plus 1. So what we need to do is we need to find the slope of this line g of x, that is g dash of x, which is basically f of xi minus f of xi minus 1 divided by xi minus 1. Also, since we have 3 points here, f of xi plus 1 minus f of xi divided by xi plus 1 minus xi equals to g dash of xi as well. From the graph on the left hand side, we can notice that f of x of I plus 1 equals 0. So substitute this in the second equation. We get x of I plus 1 equals x of I minus f of x of I by g dash of x of I. This fourth line is in the form of Newton's method. But in this case, we can evaluate g dash of x of I using the first equation as shown here. The iteration stopping criteria is the same as we have seen before, that is modulus of x of I plus 1 minus x of I should be lesser than or equal to epsilon 1, which is our tolerance criteria, which is a very small value. Or we can use f of x of I plus 1, the absolute value, should be lesser than or equal to epsilon 2, which is another tolerance value we set. Some examples which we have seen before are given here. So once f of x is known, we need to find out, based on the two initial values x of I and x of I minus 1, we need to find out the slope of the secant, or the slope of the line joining these 2 points on the curve. So that is g dash of x of I equals f of x of I minus f of x of I minus 1 divided by x of I minus x of I minus 1. So once we evaluate this slope, we can find out the next point, that is x of I plus 1 equals x of I minus f of x of I divided by g dash of x of I. And this procedure needs to be repeated. And at some point of time, we should be able to find the solution close to the exact solution. Now let's look at the Matlab program to solve this two nonlinear equations using secant method. The first one is the algebraic equation. So since we need to know two initial values, x of 1 I just assumed as 0.0 and x of 2 I just assumed as 2.0, and the number of iterations n is set at 100. The algorithm for the secant method is given over here, which we have already seen. It is similar to Newton's method that we have seen before, but in this case this g dash of x can be evaluated algebraically. We don't need to find out the derivative of the function f of x. So we run this, and it takes about 8 iterations to solve this problem, and the final solution came out as 0.381966, and at this value f of x is almost 0. We can look at it graphically. So when we plot this f of x function, we notice that although there are a couple roots here, one root over here, two roots you can see, and maybe another root coming further down. So we can look at the root. One root over here is 0.383, and that's close to what we obtained numerically. In fact, this numerical solution is more accurate than what we observed graphically. Now we try to solve the second equation, the nonlinear transcendental equation. So this time it took about 11 iterations to solve this problem, and the final solution came out as 1.678347, and at this value of x, the f of x is almost 0. We can look at it graphically. 7. So again there are a couple of roots here. So the one root we were able to solve is over here, 1.6768, and that's what we got over here numerically. So many times, we may not be able to solve all the roots, but it will, based on the initial values, it will generally we'll be able to solve the root closest to the values we picked. To summarize, in this video we presented secant method to solve nonlinear equations. Previously we have used other iterative methods, open domain methods such as fixed point iteration as well as Newton-Raphson's method. So the second method is the third method, third open domain method that we have seen. And the one advantage of second method is that we don't need to obtain the derivative or evaluate the derivative of the function f of x. When it is not easy to evaluate the derivative of the function f of x, second method can be easily adopted. But second method requires two initial points. In Newton's method, we initiate the problem with a single x value. When in second method, we require two initial points, two x values, x1 and x2, something like that. If you have any questions, please post it. Thanks for watching the video.